All right, everybody, welcome back. We proceed in our course here on compressible flow. And let's see, last time we provided a bit of an introduction to compressible flow. We talked about stagnation states. And how we have properties like that are defined at that state, like the stagnation enthalpy, which we actually derived an equation for when we're dealing with gases, which is just the enthalpy plus v squared over 2, which sort of represents the kinetic energy of the gas. We also have the Mach number, talked about that, m equals v over a, and then we also derived sound speed a, which is equal to the square root of gamma RT for perfect gases. Okay, and you know, I wanted to actually do this in the last lecture, but I often like to bring in the historical context. I think I did so in the first lecture when we talked about Clausius. But I wanted to have a moment to talk about Ernst Mach. And so I'll scroll over here to these images I have. There's a photograph of him. And then below that photograph, you can see the image that represents the experimental work that he did that resulted in the Mach number bearing his name, this is a Schlieren photo of a bullet traveling through the air, and you can see the shock waves that are formed because the bullet is traveling faster than the speed of sound in the medium, and so you know that's perhaps his most celebrated contributions, but he also had a lot of very interesting work that he did throughout his life, some of which even had to do with philosophy. So he had this I think they called him something like a scientific philosopher, but he had this idea which had to do with like this I forget exactly what it was called, but the idea was that he only believed that sensations were real, and so that was the only thing that you could verifiably say is real, almost to the point where at one point he was at a lecture of Boltzmann on I presume statistical mechanics, talking about the physics of atoms and atomic theory, and he stood up and declared that he did not believe in atoms because you couldn't they weren't something they could be directly observed, and so therefore they may not be entirely real. So he didn't believe that it existed. This sort of thinking brought him to a lot of ideas. Like, for example, he independently discovered the inner ear balance relationship. So he's one of two people who simultaneously worked out the mechanism by which that happens by using this apparatus. You can see on the bottom right here, it's like a 3-axis swivel chair that he used to make that discovery. And then I wanted to include this self-portrait he made here, which is interesting. So it's called a self-portrait. It's an engraving, but you can see that it's it's drawn from literally his perspective of his eye. You can see sort of his nose here and his mustache as he's looking down through his left eye at his body as he sits on this lounge chair and draws this self-portrait. So it gives you an idea of kind of the type of mind that he had. Very interesting. Another couple of interesting, one interesting fact that I saw was that he's the godfather of Wolfgang Pauli, which those of you who study physics know who Pauli is. Very important forefather of quantum mechanics. And so he had these very interesting ideas, and you know, although those ideas were opposed to some nascent theories that would become very important, like atomic, the theory of atoms and statistical mechanics, His thinking would actually inspire Einstein's own thinking that led to his theories of relativity. So he's often credited as a precursor thinker to Einstein that led to that school of thought and eventually Einstein's great breakthroughs and sort of overthrowing of Isaac Newton in the early 20th century. So very interesting guy, but I always like to make sure that we include those historical bits of background so you can really appreciate the people who came up with these ideas that we'll be going over in our class. So with that historical background in mind, let's express some thermodynamic relations in terms of the Mach number. Okay, so I said many times that the Mach number was going to become this parameter that was extremely important and used all over the place, right? Well, part of that is because we're going to find useful ways of expressing all of these thermodynamic properties and relations in terms of the Mach number. Okay, so thermodynamic relations in terms of the Mach number. Okay, so first let's take a look at continuity. Now we talked about how for steady 1D flow in a channel, for steady 1D flow in a channel, m dot, which is equal to rho AV, is constant, right? Well, for a perfect gas, rho is equal to P over RT, and V is equal to N times A, which is just N times the square root of gamma RT. So what we can do is we can actually rewrite the mass flow rate in terms of the Mach number as m dot is equal to P A M times the square root of gamma over RT, and say that that thing is equal to a constant. And that's just one way of writing it. There are other ways of recasting it, but that gives you a little bit of a taste of how you can kind of insert the Mach number in there and do a little bit of algebra to move some thermodynamic properties in or out of an expression. In this case, we brought the pressure in as opposed to density, as well as the Mach number. We can also look at the stagnation properties that we talked about last time. Okay, let's maintain our highlighting conventions. So, recall from our last lecture that we defined HT as H plus V squared over 2, of course, just for gases. And then we can just substitute our definition of M in for V, and you end up with H plus M squared gamma RT over 2. Okay, that's something to keep in mind. We also have that, and I think that we discussed this, that that the difference between CV, so also recall that CP minus CV is equal to R, right, for our perfect gas, and also gamma is equal to CP over CV. So we can actually recast CP in terms of gamma and R. So that would be, sorry about that, that would be gamma R over gamma minus 1. You can use those two relations together to do that. So what we can do is we can rewrite sort of gamma R as CP times gamma minus 1, and that allows us to write HT as H plus M squared over 2 times gamma minus 1 times CPT, right? So that's this guy coming in there, okay? But the question is, okay, well, what's CPT, right? We're talking about a perfect gas. Well, that is the enthalpy, right? Because remember that CP is equal to the partial derivative of the enthalpy with respect to temperature at constant pressure. And for a perfect gas, you can recover enthalpy just as CPT, because for a perfect gas, CP is a constant, right? So we substitute that in there, and then this allows us to write the stagnation enthalpy in terms of just the Mach number and the ratio of specific heats, right? So because if CPT is H, we can factor that out and obtain H times 1 plus gamma minus 1 over 2 m squared, and then that is a relationship that you will use probably over 100 times in this class, right? The gamma minus 1 over 2 times m squared term will become burned into your mind by the end of this course. And I also want to point out that we're dealing with a perfect gas, right? So HT is just equal to CPTT, or CP times the stagnation temperature. And this relationship is the same thing as writing the stagnation temperature expressed as the static temperature times 1 plus gamma minus 1 over 2 m squared. Okay, two very important equations. That's why we're framing them a la David Lazzati. So you will be using these equations very frequently. You'll use these frequently. Okay? All right, so now the transition between the static state and the stagnation state is isentropic, right? So what can we say about the ratio of PT to P, right? So the process P to PT, say, is isentropic. So what can we say about P T over P? Well, this is where, again, we're going to use that isentropic relation, which is that P times V to the gamma is a constant. So we can rewrite this as, by using fractions between the stagnation state and the static state, we can write this new sort of relationship, which is PT over rho T to the gamma is equal to P over rho to the gamma, because they're both equal to the same constant. Okay, then we rearrange to PT over P. That's going to be equal to the ratio of the densities raised to the gamma. And we can use the ideal gas law to simplify that even further. Bring the pressure back in. So now we have PTT over PTT raised to the gamma. All right. Then we take that PT over P to the gamma and move it over to the left-hand side. So therefore, we have PT over P to the 1 minus gamma, right? And that is equal to the ratio of stagnation temperatures, the stagnation temperature to the ratio of the stagnation temperature to the static temperature raised to the negative gamma. I flipped the fraction there, that's where the negative comes from. And then we can then finally write that Pt over P is equal to the ratio of the stagnation temperature to the static temperature raised to the power gamma over gamma minus 1, right? And we just found Tt over T, just a couple of lines above. And so that allows us to write the ratio of the stagnation pressure to the static pressure, or in fact, we can just write the stagnation pressure as a function of the static pressure in the following way, where we have Pt is equal to P times the quantity, 1 plus gamma minus 1 over 2 times m squared over, or sorry, raised to the power gamma over gamma minus 1. Okay? So that is another very important relation that you will use very often and have to keep in mind. Okay? Another nice important one. So these sort of, really it's the relationship between the stagnation temperature and the static temperature, and the relationship between the stagnation pressure and the static pressure. Those two you're going to see over and over and over and over again. So really commit those two to memory. Okay? So this is nice. Those are some great sort of easy to derive, but also very useful relationships. Now let's talk about varying area flow. And you'll often, see this topic discussed as the area Mach relations. Okay? So we're going to simplify our analysis, okay? So we're going to consider a 1D steady flow where we have that there is no heat transfer, and we have that there are no losses. dSi is equal to 0, right? So no heat transfer means that dSe is equal to 0. So these two together tell us that this process or this flow is isentropic, right? We also have that there is no work being done. So delta W is equal to 0. And we're going to ignore potential differences. dZ is equal to 0. Okay? So let's start with our energy equation, okay? So if we start with the energy equation, we see the following, which is dQ is delta Q is equal to delta S plus dH plus dV squared. This is the differential form of the energy equation, plus G dZ. Now we just said in our assumption that this term is going away, as well as this term and this term. And so we end up with the relation dH is equal to V dV. Okay, once we apply that total differential to that V squared term. Okay, so now let's bring in the first second law of relation, that fundamental thermodynamic relation. Bring in TdS relation, where we have a du is equal to TdS minus P dV, right? We can sub in our definition of the enthalpy to bring in dH is equal to TdS minus V dP. Now remember, we assumed adiabatic and no losses, so therefore ds itself actually goes to 0, right? And we end up with just that dH is equal to V dP. And then these two relationships together tell us that dV, that's the total differential of the velocity, is equal to 1 negative 1 over rho times V dp. Okay, all right, so this is just a differential relation, a relationship between two total differentials. We're going to label this star, okay, because we're going to come back to it. So keep that one in mind, and we're going to proceed from here. All right, so we're now going to take a look at continuity. Remember, write out the whole word here. It's continuity. Remember, we're talking about 1D steady flow, so this is just that m dot is constant. Right, so let's take the total differential of each component of that. So let's take d of rho AV. That is just chain roll, right? So we are going to have AV d rho plus rho A dV plus rho V dA. And that whole thing is equal to 0 because the mass flow rate is not changing. So d of that thing should be equal to 0. You can, if you divide all three terms, or both sides of this equation, by just rho AV, you obtain this equation, which is d rho over rho plus dA over A plus dV over V is equal to 0. Okay? And we're going to denote or label this equation with a dagger. Okay, because we'll return to that one as well. Okay, so now let's sub in the dV we found in star, right? And we obtain d rho over rho plus dA over A. Let's see, in star 2 dagger to be precise. dA over A is equal to dP over rho V squared, right? And we moved it over to the right-hand side of the equation, so that that dealt with that negative sign there. Okay, so now we take a moment and we recall that A squared is equal to dP d rho, partial derivative of the pressure with respect to density at constant entropy. Now, we're dealing with an isentropic process. So here we assume ds is equal to 0. So A squared can equivalently be written as dP d rho. Okay, as like a total derivative. Now, so I told you before that we shouldn't write derivatives as quotients, or we shouldn't treat total differentials as something that can be divided by one another to form derivatives. With the caveat being that when the function is when the function being differentiated is a function of one variable only, our two definitions are compatible, and we can split the derivative. And again, it's still a hand-wavy argument, but in the limit, this works. So dP then becomes equal to A squared d rho, right? And so we can now sub this into dagger as well. And what we end up with is dA over A being equal to 1 over m squared minus 1 times d rho over rho. Okay? And that is because we've taken the the dp, and we've substituted it into the right-hand side of that second last equation that we found, this one right here, right? And once we sub that in there, we have an a squared over v squared, that's 1 over m squared. And then so then you have a d rho over rho times 1 over m squared, and then just the d rho over rho on the left-hand side, so you can see how that simplifies here. And then this allows us to relate the changes in density, d rho over rho, to the changes in area as m squared over 1 minus m squared. Okay, times dA over A. Right? So relating density changes to changes in area. Okay, and then we can kind of keep circulating this within that dagger equation. So go back to dagger sub in to relate dA to dV, right? So that we can do that here. We have m squared over 1 minus m squared times dA over A plus dA over A plus dV over V equal to 0. That tells us that dV over V is equal to 1 over m squared minus 1 times dA over A. We'll square this one as well. And again, use star this time to relate dP and dA, right? So that looks like having minus 1 over rho v squared dP being equal to 1 over m squared minus 1 dA over A. So that was taking just the previous equation there. And that tells us that dP is equal to rho v squared multiplied by 1 over 1 minus m squared times dA over A. Okay? So now that we have these relationships, I know that they seem a little archaic perhaps, but now it's actually about to get a little interesting. Okay? So first, let's consider how, consider low Mach number flows. Let's say where m is sort of smaller than 0.3, about, okay? In that case, you're going to have d rho over rho is equal to, and you can see on the top, this equation here is what I'm referring to, right? D rho over rho will be equal to something on the top, which is small. So I'm going to use this order notation. So this is a small size. This big O notation is just a notation we use when we're discovering or talking about the size of different mathematical terms and asymptotic limits. So we're saying that the top of that quotient is small, but then the bottom of that quotient is sort of order 1, or it's about the same size as 1, right? Because you have m squared is very small, and you're doing 1 minus something small, so it looks like 1. So you have that whole thing, which is something small, divided by something that's approximately 1 times dA over A. And what does this tell us? Well, it tells us that density does not change much with area variation. In other words, the flow is approximately incompressible. Right? So why is water basically incompressible? Well, it has a very, very high density. And that very, very high density results in a very, very high speed of sound, right? It's not rarefied at all. So whenever a disturbance occurs in water, it propagates very, very, very quickly, right? So basically, any sort of flow in water has a Mach number approaching 0. It's very, very small. So for very, very small Mach numbers, you shouldn't, if you change the area of a duct, you won't actually be changing the density of the water very much. And so that's where we can make that incompressible assumption. Well, so you know, in this scenario, you have things that behave the way that we expect. So thus we see behavior like V1 over V2 is equal to A2 over A1, right? And that comes from taking rho AV at state 1 and setting it equal to rho AV at state 2, and then noticing that rho 1 and rho 2, setting those equal to each other so they fall out, right? So basically, shrinking area causes proportional speed up in flow velocity. Right? So, okay, so now the question becomes, let's look at the cases where the Mach number is approaching 1 and also greater than 1, right? So what about 0.3? I'm putting these little squiggles in here because these are not super well-defined boundaries, right? But what about Mach numbers between 0.3 and 1, as well as Mach numbers greater than 1? And we'll talk about the Mach numbers equal to 1 as well in a second, right? But let's make a little table here. So we're going to say that in this case, we're going to look at the case where dA is less than 0. What that means is that we have a converging duct, okay, with the flow going this way, okay? So those are the walls of the duct, and the flow is going to the right. And we're going to write a table where we're going to say for the Mach number less than 1 is the pressure, density, or velocity going up or down. And then this is for a Mach number greater than 1. Right, and then likewise, we'll do the same table where where dA is greater than 0. That means that the duct is expanding. Okay, it's going to higher cross-sectional area as you move to the right through the flow. Okay, let me move this this expanding duct. We'll do like this. This over, and we'll put the expanding duct here, and we know that the flow is going this way, right? And we want to talk about the pressure, the density, and the velocity, and then we have M less than 1, that column, and then m greater than 1. Okay, so then let's work our way through this, right? So let's say that the area is decreasing, so we're dealing with the left, what you might think of as a nozzle. Okay, we'll talk about why that name doesn't always necessarily refer to something that's converging, but that'll be a bit later. So in this case, when the Mach number is less than 1, what's happening to the pressure? Well, this is where we go up here and we look at these relationships, right? So we're talking about the relationship between area and pressure, dP. Okay, so let's look at this guy right here. We have that the Mach number is less than 1. That means that this thing remains positive, right? Because the Mach number is less than 1. And dA itself is negative. And rho and v are positive definite value, or v squared and rho are positive definite values. So that means that dP is actually negative in that case, and the pressure is going down as you decrease the area. Okay, and then much the same can be said about the density. If we look at this relationship up here, pointed out with the red arrow here, dA is negative, m is less than 1, so this thing is positive, this thing is negative, and therefore we end up with d rho being negative, and therefore the density is going down for Mach numbers less than 1. And then let's look at the velocity. The velocity, dv, for a negative dA and an m squared less than 1 is actually positive, right? Because we have m squared minus 1. If m squared is smaller than 1, then that thing is negative. And then dA is said to be negative. So therefore, you have two negatives multiplied by each other, and you end up with dV being positive. Okay, so small duct getting smaller, flow speeding up. That's actually the behavior that you're familiar with, right? Well, let's look at the Mach number being greater than 1 case, right? This is interesting. So Mach number greater than 1. Let's look at dP. Mach number greater than 1. This term is now negative. dA is still negative, so we have negative times a negative, and then that results in a positive, and rho and v squared, like we said, are negative. So this flips sign, and likewise for rho, this term is flipping sign, and it's being multiplied by dA, which itself is negative, and so you end up with this flipping sign here. Now here's an interesting case. M squared is now greater than 1. So in the dV relation, this thing is now positive, and you're multiplying by a negative value. So the velocity, as you move through a converging duct, if your Mach number is greater than 1, it actually decreases, right? So you're pushing flow through a converging duct, the same flow rate, and the velocity is decreasing as you get to smaller and smaller velocity, smaller and smaller cross-sectional area. That is weird, okay? And that's something that occurs when you bring in this supersonic flow. Okay, so now let's look at the other case. In the other case, your dA is positive, meaning you're in a diverging duct. And in all of these cases, the dA is just a constant sort of factor that's being multiplied on the right-hand side. So we really are flipping the sign of everything in this rightmost table here. So the density and the pressure go up for Mach numbers less than 1 when you have a diverging duct, and also the velocity is going down for Mach numbers less than 1. when you have a diverging duct, which makes sense. You know, that's what you would expect. If you have a diverging duct, you expect the flow to be slowing down. Well, when you have a Mach number greater than 1, the pressure and density are going down, but the velocity is going up. So for a Mach number greater than 1, if you have a diverging duct, you could think of it as a diffuser, or something you would expect to be a diffuser, slowing down flow. It actually speeds up the flow, okay, for supersonic flow. So the overall observation is things behave seemingly opposite to what we expect when the Mach number is greater than 1. Okay? All right, and then there's this figure in the paper which kind of allows you to see everything at once. So, you know, assume the flow is driven by a large delta P, or pressure gradient, right? So dP is now negative throughout. So if you can actually plot the variation of the properties as a function of the Mach number in this case. So on this axis we have the pressure, the density, the area, and the velocity, right? And we're plotting this as a function of the Mach number. So this is fixing dP to be negative and plotting these things. The velocity has this sort of shape to it. The area has this sort of shape. So this is the area, this is the velocity. And then we have, at the minimum of this thing, we have Mach number equal to 1. This region is Mach number less than 1. This region is Mach number greater than 1. And then we have, for the pressure and the density, they kind of follow the same general trend, which is this sort of downward thing here, and then in practice sort of continues down in that, changes concavity. And you have P and rho here. Okay? So this is kind of an interesting plot. It gives you an idea of how these properties vary as you vary the Mach number. One thing to keep in mind is, or to notice here, is that the V in this graph is not a straight line, even though you think of V as equal to A times M, right? Well, of course, A itself is a function of the temperature. So the other properties here are changing as you change the Mach number, and so you actually have a non-trivial variation of V with M, because M itself is not fixed as we move through here. Okay, or sorry, the temperature is not fixed, so the speed of sound doesn't change. Okay. Nice. So that sort of gives us an idea of how these properties change as we move through a converging or diverging duct. Now let's actually talk about this idea of nozzles versus diffusers. Okay, what do these words actually even mean? So a nozzle is a device that converts enthalpy into kinetic energy. A diffuser does the reverse. Okay. So this flow, where you have a diverging duct with the flow going this way, where m is greater than 1, is a nozzle. Okay, it's not a diffuser. It has a diverging area, but the Mach number is greater than 1, so it's a nozzle. If the Mach number is less than 1, then it's a diffuser, like you're familiar with, where the velocity of the flow is decreasing as you move through the thing. Okay, so now here's the question. Can this thing, which is a converging duct, the flow is moving this way, can that thing accelerate flow beyond m equals 1? Is that possible? Take a minute to think about this, pause the video. Is this possible? Right? And thinking about really just taking a look at this table here, right? So that's a converging nozzle. So when the Mach number is less than 1, the velocity accelerates as it moves through the device. But as soon as you hit Mach number equal to 1 and start to move beyond that point, the velocity is required to decrease as it moves through the device, as the area gets smaller. So the answer is no. Anytime the Mach number is greater than 1, this becomes a diffuser. Or in other words, the velocity starts to decrease. So in fact, for a steady flow, m equals 1 is always attained at the plane of minimum area. At the plane of minimum area, called the throat. So how it is. Okay, so the reason for this is not entirely obvious. Okay, so let's imagine we're driving the flow through some change in pressure, some pressure gradient, right? So if we have a small pressure gradient, then moving through this converging duct, we'll have Mach number less than 1 at the beginning. Let's set that as our requirement. And then at the exits of this converging duct, we would also have Mach number less than 1 because the pressure gradient is small, right? Now, if we increase delta P from there, make it large, let's say we increase it just to the point where we hit m=1 at the exit. So we still start with m less than 1 at the entrance, but then we hit m=1 at the exit, okay? And it's pinned at n=1 at the exit, which is it happens to be the point of minimum area because this is a converging only duct, right? Well, what if we then just try to make delta P huge? We try to actually force more, force the flow to move faster here by increasing our pressure gradient, right? We're pushing it for harder, or sucking it harder on the other side, really, right? Well, what happens? We have m-1 here. Does that plane of Mach = 1 move inwards into the duct? Well, what we've shown is that it can't, right? Because if it moves inwards into the duct, there would be more converging section after it, and that would require the velocity to then start to decrease, right? So what happens actually, right, is it has to do with this idea of causality. So really what's happening physically here, so we have these area Mach relations, right, and they tell us that, you know, we can't accelerate flow beyond Mach 1 in this converging duct. But what's actually happening is that the interior of this duct, as soon as you hit Mach = 1 at the throat, it becomes blind to everything beyond the throat. Right? So the molecules are moving faster at that point. The actual molecules that you're forcing through the duct are moving faster than the speed at which information propagates. So they're running away from you faster than the information can get back. What that means is that the duct, no matter what you do to change the pressure gradient, like on this side of the duct, on the outside, right, the back pressure, if you keep on dropping that pressure down back there, it's not that bigger pressure gradient is not being communicated up through the interior of the duct that can tell the flow to accelerate more. Saying like we have, you know, we're being pulled even harder. You know, from starting from the P small, all the molecules are moving out of the way, and that information is propagating up the duct and telling the molecules that opening of the duct to like move faster, come fill this empty space, right? Well, once we hit Mach = 1, everything beyond that point is the molecules inside the duct are completely blind to that. They can't get any of that information, right? So that's why you can continue to increase that pressure gradient as much as you can. The fact is that the molecules inside the duct don't know what's happening outside, so they don't know how big the pressure gradient is. They only know that they can get accelerated to this maximum m=1 point, right? So let's write that down, a summary of that down. So the idea has to do with causality. The molecules downstream of the m=1 point, that plane of minimum area, can't communicate to the upstream molecules. That delta P is greater. Okay? So then the question becomes, how do we reach Mach greater than 1? How can we use a nozzle or varying area device to convert any sort of excess enthalpy that we've injected into our gas safe through some sort of combustion reaction? How can we utilize that to get supersonic flow? Well, that's where you get the converging diverging nozzle. So how to reach m greater than 1, the CD nozzle. Converging, diverging nozzle. Right? And so that's where we came up with this idea, where you have a duct that converges down to a minimum throat, and then it expands. Right? Oh, that was not very smooth. Let's make that a little bit more smooth. Like that, right? Where the flow moves in this direction. Right? So that's a converging, diverging nozzle, or a CD nozzle, and this entire thing is a nozzle, right? Because you're supposed to attain m equals 1 here, you have m less than 1 here, and then on the diverging side, because you attained m equals 1 at the throat, now you can accelerate the flow through the diverging section, right? So that we're going to talk about these converging, diverging nozzles in so much detail. It's going to be a big portion of the course, okay? So we'll talk about them later, address details of these later. But for now, you know, that gives you an idea of what's happening here. So the point is that we can try to use these varying area ducts as a mechanism to increase the speed of our flow, convert the excess enthalpy that we have into kinetic energy. But we can only do it to a certain point with just a converging duct. We have to add that diverging section to push it beyond the sonic condition. Okay, so now we're going to kind of take a break, or not take a break, but dive back into the actual math. Take a break from drawing a bunch of diagrams. And we're going to talk about what are called the working equations. Okay, so what do working equations refer to? So that term, working equations, refer to this relationship between two different states in a 1D flow system, where you have the relationship between two properties, say the pressure at state 2 to the pressure at state 1, are just only a function of the Mach number at state 1, the Mach number at state 2, the ratio of specific heats of the working gas, and any irreversible losses. Okay, that's a SI here. SI. So what we do is we find a way to express the change in a certain property between two different states as just a function, essentially, because in most cases we're going to be ignoring losses, as just a function of the two Mach numbers between the two states, right? So in general, we're just restricting ourselves, so that this will be for a steady 1D flow with no heat, no work, and no potential changes. Okay? But we are allowing for some losses here. Okay, so let's talk about temperature first. Okay, so for a perfect gas, we know that H is just equal to Cp times T, and HT is equal to Cp times TET, right? That's the specific heat times the stagnation temperature. Our process, our overall process, between state 2 and 1, let's assume that that's isentropic, okay? So now we are going to restrict ourselves to the case where delta SI is equal to 0. So assume dSi is equal to 0. That allows us to say that the overall entropy does not change. And so we know that in this case, HT1 is equal to HT2. Oh, whoops, sorry, we actually don't need that. Remember, we had that all we need for the stagnation enthalpy to remain constant was for it to be the process to be adiabatic, right? Yeah, adiabatic system and no work, and the reason we saw that from the energy equation between arbitrary states. Okay, so we know from energy equation that for delta Q, delta W S equals 0, that implies that HT is a constant. So that means that we know that HT1 is equal to HT2, and because we're in a perfect gas, TT1 is also equal to TT2. Well, earlier in this lecture, we derived the relationship TT is equal to T times 1 plus gamma minus 1 over 2 times m squared. And that allows us to write down the relationship between T2 and T1, because TT2 is equal to TT1, as the ratio of 1 plus gamma minus 1 over 2 m1 squared over 1 plus gamma minus 1 over 2 m2 squared, right? So that's how the temperature changes between two points as a function of just the Mach numbers. Let's also, we know that PT is equal to P times 1 plus gamma minus 1 over 2 m squared raised to the gamma over gamma minus 1, right? And we talked about, when we talked about the stagnation pressure energy equation, we showed that PT2 over PT1 is equal to e to the minus delta S over R, right? So we can say that P2 over P1 is equal to the quantity 1 plus gamma minus 1 over 2 m1 squared over 1 plus gamma minus 1 over 2 m2 squared raised to the power gamma over gamma minus 1 times e to the negative delta S 1 to 2 over R. Okay? So that would be our working equation for pressure. And we can use these results. We can use these with, sorry, it's getting a little messy here. Use these with continuity to relate A1 to A2, right? So we have that rho 1 A1 V1 is equal to rho 2 A2 V2 because the mass flow rate is constant. That allows us to write the ratio of A2 to A1 as rho 1 V1 over rho 2 V2. We can bring in the definition of the Mach number here, RT2, P1, M1, A1, so we're bringing in the ideal gas law equation of state along with the definition of the Mach number. And that leaves us with P1 square root of T2 M1 over P2 square root of T1 M2, right? And we sub in those two ratios that we found just before, and we get A2 over A1 is equal to M1 over M2 times the quantity 1 plus gamma minus 1 over 2 M2 squared over 1 plus gamma minus 1 over 2 M1 squared raised to the power of gamma plus 1 over 2 times the quantity gamma minus 1, all multiplied by E to the delta S over R. Okay? And that equation might look a little unwieldy, but it actually, we're going to talk about a type of reference state called the sonic reference state in just a moment, and we'll expand on that in subsequent lectures. But once we start using that reference state, this one in particular becomes very important for propulsion system analysis. So you know, maybe put an extra little pin in this equation here. Okay, so like very simple example. And, you know, you'll be dealing with more complicated versions of this using the working equations, but assuming that the losses are negligible, you know, what area ratio is needed to increase the Mach number from 1.5 to 2.8. So, you know, if we assume that gamma is 1.4, then we get that A2 over A1 is equal to 2.98 to achieve this. And does this make any sense? And of course it does, right? Because we're starting with a Mach number that's greater than 1. So we need to expand our area to accelerate it any further, right? So this makes sense. M1 greater than 1. Okay? So there will be more complicated versions of those types of problems. Okay, and then one final thing, and we'll talk about this more in the next lecture, but I want to introduce this concept of the sonic reference state that I just mentioned a moment before. Sonic reference, that's not how I spell reference. Oh god, I'm losing it. Reference state. Okay? And we actually often denote this with a star. So a lot of people will just call it the star reference. And it will be denoted with a star for sure. Okay, so we're going to introduce a new reference state. Okay, so we've introduced the stagnation reference state, which we know is the state that you reach when you isentropically adjust your flow to V equals 0, and 0 potential too, if that's important. Now, in this case, is going to be the star reference is the state that is reached when the flow is isentropically adjusted to n equals 1. Right? So The stagnation is isentropically adjusting to the V, or also m equals 0. And now we're talking about isentropically adjusting to m equals 1. Okay, so on a TS diagram, we can draw this like this, so you can get a pictorial idea of what we're looking at. TS, which for a perfect gas is the same thing as an HS diagram, right? We have two different states here. We'll say this is day 1 and this is state 2. And there's some process whoops, let's draw a better line than that. There's some process that connects the two of them. Okay, so the stagnation state is up here at we'll call it 1T, and we know, and then this corresponds to n, like I just said. That's approximately vertical. Let's pretend that line's vertical. This is 2T. This corresponds to m equals 0. And then there's another reference state down here that corresponds to m equals 1. Right? And then this would be 2 star and 1 star. Okay, so 1T, 2T, and 1 star, 2 star. Okay. One important thing to note, let's look at our area ratio here. So if we want to look at the ratio, say, of A2 star to A1 star, right? When you have some losses between state 1 and 2. What that means is that we look at this equation and we just sub in m1 equals 1 and m2 equals 1. Well, that means that all of these quotients are going to cancel. And what you end up with is that A2 star over A1 star is simply E raised to the delta S over R. But from the stagnation pressure energy equation, I think that's where we derive the relationship between PT1 and PT2. Yes. So from the stagnation pressure energy equation, we have that this is equal to PT1 over PT2, right? So that's interesting. That allows us to say that PT1 times A1 star is equal to PT2 times A2 star. All right, so the stagnation pressure, so corresponding to state 1, times the sonic area corresponding to state 1 is equal to the same thing for state 2. In other words, that product of the stagnation pressure and the sonic area is conserved, even when there are losses. Okay, so this is an important relation that you'll occasionally use it to kind of close the system. Okay, especially when there are losses. And by close the system, I mean, add another algebraic equation that allows you to solve for all your unknowns. It also allows you to reason about what's going up and what's going down in cases where you have losses. So you'll probably return to that relation fairly often. Okay, so think of that as a little bit of a preview into our discussion of sonic states, which we'll pick up next time. But for now, thank you for watching and listening, and I hope you have a great day, and I will see you next time.